Hello friends, my name is Divya Srivavi, working as Assistant Professor in the Department of ECE SJBIT. In this lecture, we'll be discussing about the angle modulation. So these are the topics we'll be covering on this module. So let us see what is the basic definition of angle modulation. Angle modulation, it is nothing but the angle of the carrier wave is varied in accordance to the baseband signal. So here amplitude modulation in that we have varied the amplitude of a sinusoidal carrier wave in accordance with the baseband signal. So this is the second family of a continuous wave modulation system, namely the angle modulation. So here amplitude is constant, and here there are two types of angle modulation. One is phase modulation and another one is the frequency modulation. In angle modulation, here it is a process in which angle of the carrier wave is varied in accordance with the baseband signal. In this method, amplitude of the carrier wave is maintained constant. So here we can have a better discrimination against the noise and interference compared to the AM, but what is the main drawback is the increased bandwidth. So we'll begin with the study of angle modulation by writing the modulated wave in the general form. That is S of t is equal to AC into cos of theta I of t. So where theta I of t, it is the angle of a modulated sinusoidal carrier signal at time slot t. We'll assume that the function of the message signal is S of t. So this is the general form of angle modulated wave. So what is AC? AC is the carrier wave amplitude, and the complete oscillations of the carrier wave, it will be occurring when theta I of t, it is changing by 2 pi radians. So if theta I of t, it is increasing monotonically with the time, the average frequency in the hertz over the interval t to t plus delta t, we can plot it like this, where x-axis is given by t and y-axis is given by theta I of t. So it varies linearly. So f delta t of t is given by theta I of t plus delta t minus theta I of t divided by 2 pi into t plus delta t minus t. So here t and minus t gets cancelled. So f delta of t, it is given by the equation ti of t plus delta t minus ti of t divided by 2 pi t. So now we need to understand other basic definitions which we will be using. The first one, it is the instantaneous frequency. So instantaneous frequency of signal, modulated signal S of t, it can be given as Fi of t. It is represented as Fi of t. It is equal to limit of f delta of t, and f delta of t, it is the frequency equation what we have seen just now, where delta t tends to 0. So Fi of t is given by 1 over 2 pi into d differentiation of theta I of t with respect to t. So the angle modulated signal S of t can be represented as a rotating phasor of length AC and the angle theta I of t. So theta I of t, it is given as 2 pi fct plus psi of t. So what is this WC? WC is 2 pi fc. So as I said, there are two basic forms of angle modulation. One is phase modulation and another one is frequency modulation. Phase modulation, it is a form of angle modulation in which the instantaneous angle theta I of t is varied linearly with the message signal. So theta I of t is given by 2 pi fct plus phi. What is this phi? Phi is equal to kp into m of t. So the theta I of t, now you can replace it, you can represent as 2 pi fct plus, in place of phi I am replacing it with kp into m of t. So phase modulated signal S of t, we have already seen in time domain, it is AC into cos of theta I of t. So S of t is given by AC into cos of, in place of theta I of t, we will replace it with the theta I of t as 2 pi fct plus kp into m of t. So what is this kp? Kp, it is a phase sensitivity constant with respect to the phase modulation. So it is expressed in phi. And what is the unit? Unit is volts, radians per volts. So what is 2 pi fct? It is the angle of the unmodulated carrier wave. The other form of angle modulation is frequency modulation. It is a form of angle modulation in which the instantaneous frequency is varied linearly with the message signal m of t. So the instantaneous frequency fi of t is given by fc plus kf into m of t. What is fc? Fc is the frequency of the unmodulated carrier and kf is the frequency sensitivity factor, which is represented in terms of hertz per volts. So now we will integrate the equation 1 fi of t on both the sides between the limits 0 to t. So, and we are replacing fi of t is equal to 1 over 2 pi into d theta I of t by dt. This we have already seen. So, replacing fi of t by this equation and integrating the equation 1, we will get this equation. So, after integrating and all, we will be able to reduce theta I of t is equal to 2 pi fct plus 2 pi kf integral 0 to t m of t into dt. So it is assumed that the angle of unmodulated carrier wave, it is 0 at t. So this frequency modulated signal, it is given as S of t is equal to AC into cos theta I of t. So we are replacing this theta I of t by the equation just now what we have reduced. So S of t is equal to AC into cos of 2 pi fct plus 2 pi kf integral 0 to t m of t dt. So this is a waveform representation. This is a carrier signal C of t, which is a very high frequency signal and which is having a constant amplitude. And this is a message signal which is a low frequency compared to the carrier frequency. And this is what is the AM signal. We have studied in the previous module how AM signal is generated. So we are looking into the PM and FM in this module, especially FM. So this is the waveform. Whenever there is a positive peak, there will be a accumulation, or you can say dense frequency at this point. Whenever there is a negative half cycle, there will be a sparse frequency, means very less frequency at that point, right? And this is the waveform of PM. So now let us understand what is this frequency modulation. So the frequency modulation S of t, it is given by, just now we have seen AC into cos of 2 pi fct plus 2 pi kf into integral 0 to t m of t into dt. So it is basically a non-linear function of the modulating signal m of t. So we can also call the frequency modulation as non-linear modulation process. So let us consider the message signal as m of t is equal to am into cos 2 pi fmt. So the instantaneous frequency, it is given by fi of t is equal to fc plus kf into m of t. Kf, we know it is a constant. Fi of t, we are replacing m of t with the equation of the message signal, where you can see kf into am. So this is nothing but your frequency deviation. What is frequency deviation? It represents the maximum departure of the instantaneous frequency of the FM signal from the carrier frequency fc. So the frequency deviation delta f, what we have seen, it is proportional to the amplitude of the message signal. Frequency deviation delta f is proportional to the amplitude of the message signal, and it is independent of the frequency of the message signal. We don't have any factor related to f, frequency. So the instantaneous frequency, it is given by fi of t is equal to 1 over 2 pi into d by dt of theta I of t. So integrating this equation on both the sides and substituting the third equation in the fourth, we will get this equation. After continuous solving, we will get theta I of t is equal to 2 pi fct plus delta f by fm sine of 2 pi fm t. So the ratio of frequency deviation to the modulating frequency, we call this as a modulation index of FM signal. So now how do we represent the modulation index? It is represented as beta. Beta is equal to delta f by fm. So now theta I of t, in terms of beta, it is represented as 2 pi fct plus beta times of sine 2 pi fm into t, where beta is the phase deviation and it is measured in radians. So what is the final equation of fm? Fm is s of t is equal to ac into cos of 2 pi fct plus beta times of sine of 2 pi fm into t. So now depending on the beta value, we will have two cases of frequency modulation. One is narrow band FM, another one is the wide band FM. Narrow band FM is when beta is very small compared to 1 radian. Wide band FM is the case where beta is very large compared to 1 radian. So now we will take up narrow band FM and wide band FM. Narrow band FM is a case when beta is very small compared to 1 radian. So let us consider a signal s of t is equal to AC into cos of 2 pi fct plus beta into sine of 2 pi fm into t. So we have the equation cos of A plus B. So let us take A is equal to 2 pi fc and B is equal to beta times of sine 2 pi fm into t. So we know the formula cos of A plus B is equal to cos A cos B minus sin A sin B. Expanding this equation, we will get s of t is equal to AC into cos of 2 pi fct into cos of beta times sine of 2 pi fm into t minus AC into sine of 2 pi fm into t into sine of beta times sine of 2 pi fm into t. And we know that in a narrow band FM, beta is very small compared to 1 radians. So cos of beta times sine of 2 pi fm into t, here in this case, since beta is very small, it will be equal to 1. Means cos of very small value is equal to 1. Sine of very small value is equal to that small value itself. So assuming these two conditions, substituting these two expansions in the equation 2, will get s of t is equal to AC into cos of 2 pi fct minus AC into sine of 2 pi fct into beta times of sine of 2 pi fm into t. Now we will just rearrange the terms. S of t is equal to AC into cos of 2 pi fc into t minus AC beta into sine of 2 pi fct into sine of 2 pi fm into t. So now if you observe that the equation, it is similar to sin A sin B. Observe here, it is sin A sin B. So we will expand this term. What is sin A sin B? Sin A sin B is equal to 1 by 2 into cos of A minus B minus cos of A plus B. So using this relation, we can write s of t is equal to AC into cos of 2 pi fct minus beta into AC by 2 cos of 2 pi fct minus 2 pi fm into t minus cos of 2 pi fct plus 2 pi fm into t. Now multiplying this constant term with the individual terms, we will get AC into cos of 2 pi FCT minus beta AC by 2 into cos of 2 pi. Here we are taking 2 pi common, so left out term is 2 pi t common, left out term is FC minus FM. Similarly, in this term also we will take 2 pi t common, so the remaining term is FC plus FM. If you observe the equations now, if you compare this equation with the amplitude modulated wave, which is S of t is equal to AC into cos of 2 pi FCT plus mu AC by 2 into cos of 2 pi FC minus FM into t plus mu AC by 2 into cos of 2 pi FC plus FM into t. If you observe this equation, the only difference between this narrow band FM wave and this AM is just the sign reversal. Here it is minus, here it is plus, here it is plus. Okay, it is just the sign reversal of the lower side band. Only here we have a sign reversal. So thus we can say that a narrow band FM signal, it requires the transmission bandwidth which is same as that of your AM signal. So what is the bandwidth occupied by AM signal? It is 2 times of FM. So we can say that narrow band FM also occupies the same bandwidth 2 times FM. Next is the wideband FM. In wideband FM, here the beta is very larger value. So it is AC, this equation what we have, we can use a complex equations e to the power of j theta, it is equal to cos theta plus j sin theta. Substituting that here, we are taking only the real part of that equation. So real part of AC cos of, here we are substituting it as e to the power of j 2 pi FCT plus beta times of sin 2 pi FM into t. So substituting this, we will get S of t is equal to real part of e to the power of j 2 pi FCT into S cap of t. So what is S cap of t? S cap of t is a periodic time function with the fundamental frequency Fm. So S cap of t is represented as n is from minus infinity to infinity summation Cn into e to the power of j 2 pi n Fm into t. What is this Sn? Sn is a complex Fourier coefficient which is given by Cn is equal to Fm integral minus 1 over 2 Fm to 1 over 2 Fm S cap of t into e to the power of minus j 2 pi n Fm into t. Substituting Cn here, substituting S cap of t here, so we will get this equation. So we will assume that x is equal to 2 pi Fm into t and we are differentiating dx by dt, it is equal to 2 pi Fm. So we can say that dt is equal to dx by dfm. So we are changing the limits here. So when the limits are changed, the new limits is x is from minus pi to plus pi. So the equation now becomes Cn is equal to AC into Fm minus pi to plus pi e to the power of j beta times of sin x minus n sin x nx dx by 2 pi Fm. This is what is the limits we get. So after solving, and we are taking the Bessel's functions of first kind in order with respect to the argument beta into account, Cn is equal to AC times Jn of beta. Jn of beta is the Bessel's function. So substituting that S cap of t, now it is equal to n is from minus infinity to plus infinity AC into Jn of beta e to the power of j 2 pi n Fm into t. So after solving this, we will get S of t is equal to AC n is from minus infinity to plus infinity Jn of beta into cos of 2 pi into Fc plus n Fm into t. So now if you expand this above equation with respect to n is from 0, 1, minus 1, 2, minus 1 till infinity, plus infinity and minus infinity, we will get this equation S of t in terms of the Bessel's equation, Bessel's functions J0, J1, J minus 1, J2, J minus 2, like this it goes on. So now just rearranging these terms will get you the equation thus. So if you observe this equation, the modulated signal, it is having a carrier component AC component and it has infinite number of side frequency, that is one is at plus FM, minus FM, plus 2 FM, minus 2 FM, like that it goes on till the infinite number. So now from the properties of the Bessel's function, we know that for any even n values we can have Jn of beta is equal to minus 1 to the power of n j minus n of beta. For odd values, Jn of beta is equal to minus j minus n of beta. So substituting this, j naught of beta is equal to 1, j1 of beta is equal to beta by 2, like this we can deduce it. So after taking the Fourier transform, the final equation is S of f is equal to j naught of beta into AC by 2. We have taken the Fourier transform, so we have a delta function here, delta of f plus fc plus delta of f minus fc. This is for j naught. Similarly, j1 of beta into AC by 2 into delta of f plus. Now the frequency is situated at plus fm and minus fm, fc plus fm, fc minus fm, like this, and then j2 of beta. Similarly, it goes on like this. So when we plot the spectrum of the FM wave, it is looking somewhat like this, which is having the function at fc minus fc, fc plus fm, fc minus fm, minus fc plus fm, minus fc minus fm. Similarly, fc plus 2fm, minus fc minus 2fm, like this. So what is the meaning is, it is having a infinite number of side bands. So this is what is the Bessel functions looks like, and this is the spectrum of the signal. When you are having different beta value, when beta is 1, this is what is the spectrum, when beta is 2, like this, when beta is 5, this, that is the modulation index. So this is the spectrum. So we will stop at this point. In the next video, we will be continuing with the power calculation.